simultaneous core partitions into distinct parts.
Naive. Okay. So I think all of you know what a partition is, right? So if you have a non-negative integer, a partition is a way to write that as a sum of non-negative integers. So for my example, I'm going to use this partition of 9. So one way to partition 9 is you say 9 equals 4 plus 3 plus 1 plus 1. So, you know, the order does not matter, so we can assume they're decreasing or not increasing. And so also there's the way to make a diagram for this partition, so the Young diagram. Says we're going to draw this partition by just making a bunch of rows of boxes where the ith row is the size of the ith part. So the Young diagram for this would be the first row is going to have 4 boxes. And then the next row will have 3 boxes. And then you have 2 rows with 1 box. So that would be the Young diagram for that partition. Okay. And so now I'm going to make this definition called the hook length. So for each box, you have an associated hook length. So now I'm going to add to this diagram the hook lengths. Okay. So a hook length of box is just, you take your box and you count the boxes below and the boxes to its right, and then you add 1. So it's just the length of this hook. So for example, the hook length of this box, we just count all of these boxes. So hook length of this box would be 1, 2, 3, 4, 5, 6, 7. And then as you fill in the rest, you get 7, 4, 3, 1, 5, 2, 1, 2, 1. So those are the hook lengths of all the boxes in the Young diagram. Okay. So any questions about that? Okay. And now, so another definition. An ST core partition.
May I start with S partition?
Okay, right, I'll start with just that. So before I do that, just a plain S core partition. So an S-car partition is one that avoids hook lengths of size S. So S-car partition, no hook length of size S. Okay. So for example, looking at this partition, this would be 6 core, right? It would not be 2 core. Because there's no, 6 does not appear in this Young diagram, but 2 appears over there. So it's not there. And then, like the title says, you can have simultaneous core partitions, which are just partitions that avoid multiple hook lengths. So an ST core partition means no hook lengths S and T. And it has to avoid both of those hook lengths. So going back to here again, this would be 6, 8 core. But it would not be 6, 7 core. Because even though it avoids 6, it has a 7 over there. Okay. So any questions about that? Yeah.
Do you not care about whether or not the S and T are minimal? Like it's a 9-10 core. Right?
Right. Oh yeah. So obviously it's many things, and so yeah, it is 9 to 10 core.
Do we care in particular about the minimal choices there?
I mean, I don't know in general if you do, but for this paper, no.
Okay.
We're focusing on like specific, like for example, in our paper, we're going to look at S plus 1 core partitions.
Cool.
So just some notation to make things easier for later on. I'm going to let P sub ST be the set of all ST core partitions. And since I'm going to write that word really a lot, I'm going to abbreviate it like that. And then if I put a tilde, basically if I put a tilde on anything, just for this talk, I'm going to use that to mean distinct parts. So PST tilde will be the same thing with distinct parts. Okay. So distinct parts, so for example, that does not have distinct parts, right? Okay. So any questions about that? Okay. So first, just some like basic theorems about these partitions. First theorem, this is by Anderson. The size of PST is finite if and only if the numbers are coprime. Okay. So the number of ST core partitions is finite if and only if S and T are coprime. And in this case, when they are coprime, there's an explicit expression for the number of partitions. So it goes size of PST is 1 over S plus T choose S. Okay. Okay. So in particular, if I were to look at S plus 1 core partitions, right? So notice S and S plus 1 will always be relatively prime, right? So if I look at those partitions, it's going to turn out that the
Nothing
number
else is 1.
What?
Nothing else is 1.
Okay.
It's still.
But anyway, other than that, this number when when t equals S plus 1 will be a Catalan number. So let me write that down. So easy corollary of this is the size of the SS plus 1 core partitions is given by, so if you just substitute t as S plus 1, you get 1 over S plus 1 times S plus S plus 1, which is S. And it's easy to show this is equal to 1 over S plus 1, 2S choose 2, which is the Catalan number. Okay, so you can count those partitions with the Catalan number.
Choose S.
Yes. Where?
Instead of choose two.
Instead of, oh yeah, this should be an S not a 2. Thank you. So any questions about that? And then the analog for when you have distinct parts. And this theorem is by, so this was conjectured by M. Deverhan. And proven by Stroud. So the analog for when now the partitions have distinct parts, but it's still S plus 1. So the number of those kind of partitions is actually a Fibonacci number instead of Catalan. Okay. So any questions about that? Okay. So the main question that we're going to be working on though is not the number of these partitions, but how does the size of the partitions behave? So like how, for example, what is the average size and the moments and so on. So this question, this was brought up by Dr. Z. So let me see. Can you guys see, or should I not use this board?
Fine.
Is
Yeah,
fine?
it's-
It's good?
Yeah.
Okay.
Like bigger.
Okay. So the question that Dr. Z started thinking about so what if we uniformly pick some partition that's ST core? And again, we're assuming that those are co-prime, so this set is going to be finite. So we're going to randomly pick a partition like that. And now we're going to define a random variable that's the size of this partition. So we'll let x of st be the size of our partition. And we view that as a random variable. And we're going to ask, what is the distribution of that? Okay. So is it clear the question we're asking? Okay. And the way we compute this is by generating functions. Well, so let's define a generating function for this random variable. GST of Q equals the sum partitions that are ST core of Q to the size of the partition. Okay. So we have our generating function for this random variable, and from this you can compute all the information you want, like the average and the higher moments. Okay. So the hard part would be, how do you compute this generating function? And so that's the part where we use Maple. And I'm not going to cover all of that, but the main idea is there is a nice bijection. So notice how we said over there that they're enumerated by Catalan numbers in a special case. So in the general case, there's actually a bijection to like generalize dict paths. So there's a bijection with dict paths. And dict paths are like easy to enumerate dynamically on Maple. So you do that and then you convert that. And that's the main idea for finding these generating functions. Okay. So once we have these generating functions, like I said, we can compute all the moments we want. So just in case, let me just quickly review how you get the moments from the generating function. So for example, the size of the number of core partitions, that would just be, you take your generating function and then you substitute 1. And then you're just enumerating 1 over all those partitions, so obviously that gives you the size of that set, right? And then to get the average, so the expected value of our random variable, you would just take the derivative, substitute in 1, and then divide by the total number. Okay. And then to get the kth moment, I may as well write this down. So the kth moment is the expected value, the random variable raised to the k. So that's going to be, it turns out you have to take this operator where you multiply by q and differentiate. You apply that k times to the generating function, and you substitute in q equals 1. And again, you have to normalize by dividing over g of 1. Okay. So if that's not clear, it doesn't really matter. The point is, once you have that generating function, you can just do these easy manipulations and get all the moments that you want. Okay. So questions about that? Yeah.
The correspondence with dict paths, does it come from the proofs of these guys, or was that new? Was that specifically for this?
Oh, okay. So that was definitely that was in a previous paper. Was it Armstrong, I think? But yeah, the correspondence with dict paths was not just invented for this. Right? Other questions?
I understand the big part.
I understand. Okay.
And Armstrong conjectures the expectation,
Okay.
and somebody else put it.
Okay. So like we just said, so it turns out before this there were conjectures for this, the expectation, right? And then I guess before Dr. Z someone did prove it, but it was not a nice proof. So it turns out, I'm going to show you, Dr. Z using some Maple, he got up to maybe I think the 6th moment or something, and it was all automated, and he actually proved explicit forms for these moments. So again, let me just overview that. Where did I put my car? So now that we can do those moments, what we can do is just crank out a bunch of them. And then fit them to, so in this case, I guess experimental evidence showed that it looked like polynomial ensembles. So now it's going to be functions of S and T, right? So you can find those moments for a bunch of values of S and T and then fit those to polynomials. And then conjecture, explicit form. Okay. And then, so in the paper, I think, let me see. So he conjectured for up to the 6th moment. And when, in the special case, when t equals s plus 1, he got it up to 9. Okay. So we got explicit expressions for these moments in terms of just s and t. It's polynomial expressions. And then that paper came out, and like I said, up to that time it was just a conjecture. I mean, it did verify this. It agreed with this. There was already a proof about the expectation, but for the higher moments, it was just like conjecture. But then after that, someone came up with like enough theory to verify that these, if you fit it to the ansatz for enough terms, it's actually rigorous. So now these can be accepted as proof. There's expressions for those moments. Okay, so later, this was proved. So we found a few things about the distribution of this random variable. So first of all, we found that x of st, so remember that is the size of a random st core partition. He found that is not concentrated about the mean. Okay, and just sort of roughly what this means, so if you have a sequence of random variables, to not be concentrated about the mean means that in the limit, the variance is getting large compared to the expectation, right? It's not clustered around the mean, so this would mean, let's see, that sigma over mu is, wait, hold on. So the variance is not getting small, so this does not go to 0. Let me just check that. So again, it means the standard deviation is big in comparison to the mean, so yeah, this is not approaching 0. Okay.
Unlike the famous normal distribution.
Yeah, so the normal distribution it would approach 0, right? So questions on that?
I mean, binomial, the sequence of binomial.
Right.
Yeah. Distribution.
So it's not concentrated on the mean, and so it's definitely not. Okay, and also he found that it's not normal, so just remember that the standardized centralized moment So in general, this sequence of just the straight moments over here, as S and T gets big, these are going to all blow up, right? So to make them more meaningful, usually we will standardize them and take them about the mean. So these moments are the expected value of your random variable minus the mean raised to the k, and then you divide by the standard deviation to the k, and that will keep them from just blowing up as the indexes get big, right? So anyway, he computed these standardized central moments, and then he took the limit as s and t go to 0, infinity, sorry. And he found that these standard central moments will limit to, so obviously if you start with the second one, it's going to be 1 because you're taking the variance over the variance. And then the third one is like approximately 1.807. And then you got 8.1429 and so on. Okay. So is everyone clear? We're taking the moments of this variable, we're normalizing them, and then we're letting s and t go to infinity. So this is the moments of the limiting distribution. Okay. So now, so it's definitely not normal because the normal distribution has moment sequence that alternate between double factorial and 0. So the conclusion, x of st is not normal since the normal distribution means that the sequence of standardized.
Xt is not asymptotically normal.
Oh yeah, so it's not asymptotically normal.
Good.
Although it's not normal for either. Yeah. It's not asymptotically normal.
Yeah, it's also so. It is not.
Because normal means that the moments approach 1, 0, 3, 0, 15, and so on. So it's a famous fact that the moments of your normal distribution alternate between 0 and products of the odd numbers, right? Okay, and obviously, so this is a rigorous proof because the moments do not agree with this, so there's no way it's going to be normal, right? So questions about that? Okay, so that's Dr. Z's work, and so pretty much in my paper, it's just extending that a little bit to now, what if we consider distinct parts, okay? So now everything's going to get replaced with a tilde. So we look at S of st tilde, and this means the size of an st for a partition with distinct parts. Okay. So, and you might expect this to will it behave like kind of the same or no? So it turns out we're going to show this. Not only is it not polynomial expressions like that, also this seems to be asymptotically normal. So adding that distinct parts makes it normal in the way. Okay.
For t equals s plus 1. No,
Yeah, just for t equals s plus 1. So right, that's a good point. So in this case, if we just try to apply that diktat thing and take out the partitions that are not distinct, it turns out that takes too long with Maple. So in this case, that diktat approach is too slow, at least the way that we implemented it. So in general for ST, we don't have any results yet. But what we did is we restricted when t is s plus 1. And it turns out, in that case, we have a really nice little lemma by Straub. So first we need to define the perimeter of a partition. So going back over here, perimeter of a partition is just the size of the largest hook length. So this is the perimeter. It's the outside boundary. Okay. And I think I can erase this better. So, definition, the perimeter of a partition is the size of the largest, well actually I can just say the largest of one. Yeah. So for example, in that example I have over here, perimeter would be 7. Okay. And so Stroud gave a characterization of S plus 1 core partitions with distinct parts in terms of perimeter. So it goes like this. So a partition belongs to P sub S plus 1 tilde, if and only if it has distinct parts, and its perimeter is strictly less than S. Okay. So, well, okay, one direction should be obvious. So if the perimeter is less than S, that means all the hook lengths are less than S. So that goes that way. And the other way is not too bad either. I think it's induction. Okay. So any questions about that? Yeah.
Analogous statements wouldn't hold for some other linear expression of S, I guess, plus 2.
No, not that I know of.
That's what's
It would be
up
nice
there.
if that did, but not that I know of, no. Okay. So anyway, this makes it easy to just do some like dynamical programs to get the generating function again. And so that's what we did in the beginning. We used dynamical program, but actually you can get this explicitly now. So I'll show you how to do that. So we're going to use a Q binomial coefficient. Okay. So real quick, this is just a Q analog of the binomial coefficient. So n choose m sub q is defined to be the product of 1 minus q to the n times the powers are going to go down until you get to 1 minus q to the n minus n plus 1. So just like with binomial coefficient, there's going to be n factors.
You want n to be on top. You have m and m.
Oh, thank you. Yeah, so n should be on top there. Okay. And on the bottom, you also have m factors. So you got 1 minus q times all the way up to 1 minus q to the n. Okay. And so this turns out this is the generating function for a certain set of partitions. So this actually equals the sum of q to the size of the partition, where the p range is over partitions with less than or equal to m parts, and each of those parts being less than or equal to n minus m.